My name is Nader Sahai, and I'm a chemist, an organic chemist, and I teach in different colleges and universities in St. Louis, Missouri. And I want to actually introduce you to a new lecture series being posted on my new channel that is about chemistry. And I want you actually to know that I believe I have a passion for chemistry, and I do believe that like math that is central to science, chemistry has a language that is central to its all different branches of chemistry. Okay, so what I want you to do is actually to follow me as I'm going to introduce the language of chemistry in a very basic form. Chemistry has actually the language of Lewis structures, and the language, there's another language that we call the skeletal forms in organic chemistry. Okay, so first we're going to talk about a series of lectures to talk about Lewis structures, and for that we actually need only two things. The first tool that we need is the idea of Lewis dot structures and actually the grand scheme geometry as outlined here in this page, as you can see. So for the Lewis dot structures, we have the group 1, group 2, group 3. We have the D gap, by the way, the transition metal or the D elements, and then group 3, group 4, group 5, all the way to group 8, which is noble gases. And you can see the way that these dots are fashioned around these elements is a unique way. As you could see, we have 4 different spots, and actually it is more clear here in xenon. So if we have all the 8 electrons, we have arranged them in 4 pairs. But if you have just 1 electron, 2 electron, or 3 or 4 electron, we just put them around in these 3 spaces, the 4 spaces that we don't see. Okay, we will talk about these spaces, which is called orbitals, later on. But if you have a 5th electron, that goes into the pairing mode, because there is no more spaces. There are only, as I just explained, there are only 4 spaces. So there is the lone pair on the top, and there is the 3 single reacting electrons. Okay, so as you could see, if we go to group 6, there are 2 lone pairs and 2 single reacting electrons. Group 7 has 3 lone pairs and 1 single reacting electrons, and group 8 has 4 lone pairs. Okay, that makes it 8. So lone pairs, there is a name, there is a reason why we call them lone or lonely pairs of electrons, because they do not want to react. They are reluctant to react. And single reacting electrons, why do we say reacting? Because they are the main cause of the reactions that form molecules, or they are the main reactivity behind making Lewis structures, covalent bonding, that we're going to talk about today in real time. So let's talk about different geometrical schemes. So when we have a molecule and we form bonds to satisfy the hunger, and all the bonds of the molecules that we actually make are to satisfy their hunger to have 8 electrons around their valence shell, or to, so to speak, to satisfy their thirst for having 8 electrons. And why we do call noble gases stable, or why we do even call them noble gases, because they do have 8 electrons around them. Okay, so that's a good reason to know why Lewis structures, why molecules form, and why Lewis structures are actually are as they are, because of the hunger of the elements to fashion or to have 8 electrons in their valence shell, except for helium that has 2, and hydrogen that actually goes to that 2. Okay, that's an exception, and we will talk about it in real time. So we will count the lone pairs after we're done, and then we count the surrounding atoms, and if the number is 2 all the way to 6, we will have a framework, and out we go from the frameworks based on then how many lone pairs I have, okay, to actually find the actual shape of that specific molecule. So it could be 0 lone pair in this framework, and it would be a linear molecule. Okay, now if you look, these pink little writings actually match when you have 0 electron to the actual framework name. Like if you have 0 electron for a molecule that is a trigonal planar framework, the name for that specific molecule would also be trigonal planar. Okay, so we will talk about this in detail with a specific example. Let's now go back and talk about specific cases. I don't know how many molecules I could cover, but I would try my best to actually do cover a lot of molecules. Okay, so let's go back to the first and most simplest molecules of all, water molecule. So water molecule is oxygen, like this. It has 2 single reacting electrons, and H2O is the formula. H2O, it has 2 hydrogen, 1 oxygen, and I will actually go and share one of the electrons in my hydrogen. Remember, hydrogen, I just told you, helium is the only element that has a valence shell of 2 electrons, and hydrogen is the only element that by sharing 1 electron will reach 2 electrons and would be satisfied. So this hydrogen is satisfied through the octet rule. Actually, that's the valence shell. And if I add a second hydrogen, that would actually satisfy that one as well. And if you look, I have actually satisfied my oxygen because there are two shared bonds, and it makes 4 electrons, and there are 4 in the lone pairs, in the 2 lone pairs that I have. And I could connect them with dots. I could connect them with bonds. Each bond represents 2 electrons. These are the covalent bonds that we are talking about. And then if I just count, I have 2 lone pairs, and I have 2 surrounding atoms, make it 4. 4 is here, is our tetrahedral framework. And if you look, if you have a tetrahedral framework with 2 lone pairs, it would be a bent shape. Okay, you could also go on and draw the water molecule like this. A tetrahedral framework with oxygen in the middle, 2 hydrogens bonded to it. Remember, the lone pairs, we just stick them to the central atom, okay? And the central atom always is the one that has the most number, or the maximum number of the single reacting electrons. Now you could see how bent water molecule is, and I could move on to yet another example, that is NH3, and I want to talk about NH3 as well. NH3, nitrogen is group 5, 1 lone pair, 3 single reacting electrons. I have 3 hydrogens, so I could just satisfy the first, the second, and as I satisfy the third hydrogen, having 2 electrons, remember that was an exception, hydrogen was the only one that actually needs only 2 electrons to be satisfied, and you could have nitrogen with 3 of these bonds, that makes 6 electrons, and a lone pair on the top that actually satisfied it with all the 8 electrons it needs. Okay, so that's the structure of NH3, ammonia. Let's go back to our framework. Let's just write down, we have just 1 lone pair and 3 surrounding atoms, make a 4. 4 was the tetrahedral framework here, up here, but in this tetrahedral framework we have only 1 lone pair. Okay, so in the exit route, if we have 1 lone pair, we will call it pyramidal. Okay, so that's why for nitrogen we call it the pyramidal structure, this one. We could actually draw it in the framework of tetrahedral as well, tetrahedral geometry as well. I could do that. Again, the lone pairs, we just stick them to the central atom, and actually you could see that we call this pyramidal. Okay, so that's how we name them. That is the name of the geometry. Where did it come from? Where I have 1 lone pair, 3 surrounding atoms, makes 4. I go to the tetrahedral framework and exit roads. Tetrahedral, the frameworks are like a highway, and the exit roads are going to actually give us these pink little names that I have that actually are the shape of the molecule. So if you have a tetrahedral geometry and there is 1 electron, one lone pair, the name would be pyramidal. Okay, so that's about NH3. Let's also talk about the CH4 molecule. There are tales of CH4 methane molecule of Auguste Kekulé, one of the prominent chemists of this time, that he actually used to keep 3D models of this beautiful molecule of methane in his work, in his office, or in his room. Okay, so carbon, group 4, has 4 single reacting electrons. I could satisfy my first, second, third, and fourth hydrogen. and by doing so I actually have satisfied all my hydrogens. And if you look, there are 2, 4, 6, 8 electrons around my carbon, and it actually have been satisfied as well. Okay, so all my atoms in the CH4 molecule has been satisfied. There are 4 surrounding atoms and there are 0 lone pairs, so 4. And then I go back to my framework here, a tetrahedral with 0 lone pair, just like the case that I told. If you have 0 lone pair in any of these frameworks, the name would be as the name for the overall framework. Okay, so the structure would be a tetrahedral. Okay, and the way I draw the molecules, the first time you draw the molecule, you can't judge the shape. Okay, you have to actually go through this step, and you don't have to actually draw it like I'm doing here. You could, but you have to go through these steps, and you have to use this grand scheme geometry going through one of those exit routes to actually come with one of these pink written structures here. Okay, so there's carbon, hydrogen, 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 and there I have the same structure is true for CCl4. There I have the tetrahedral geometrical form for a carbon. This is actually a carbon tetrachloride, but if you replace the chlorines with hydrogen, that would be the same structure for methane. I just happen to have the this one. Okay, and it is very similar to the one to the model that actually August Kekula, I told you, kept in his office. I don't know if the models were this sophisticated back then. Okay, so let's wrap up here, and I would actually post another video to actually go talk about other molecules as well.